Everybody, Miss Weeson here. Right now, you are getting ready to watch the first video from Unit 6. And so Unit 6 in AP Chemistry is largely covering the concept of thermochemistry, which is usually what we identify as the first law of thermodynamics. Now, towards the end of this unit, I do intend on doing a quick kind of brief overview on thermodynamics, which basically includes the second and third laws of thermodynamics, including entropy and Gibbs free energy. So that's what you're going to see here in this unit. Now go ahead and write Unit 6 at the top so you can kind of just keep track of things. Of course, you're always holding on to your notes as reference, and pull any other items you need to help take notes while you watch the video. Now, I'll be straight up with you. This video is a lot of vocabulary, and I say it all the time. You need to know the language to apply the concepts. And so I'll try to make this video as short as possible and not literally read to you or at you, but there is going to be a little bit of that, fair warning. All right, so when we talk about thermochemistry, we are talking about energy and energy exchange within chemical systems. Now, the term energy comes up a lot in science. You're going to hear it in physics, if you haven't already taken it, or if you have, you know what I'm talking about. Now, in chemistry, when we talk about energy, we're going to really be talking about energy on the molecular level. In other words, energy that's associated and oftentimes held within the bonds. Okay. And so what I'm going to do here is just kind of highlight some definitions, talk about it a little, and there is a couple of practice problems in this video, but again, let's just go ahead and get going. So energy, capital E is the letter we use to represent energy. And this is simply defined as the ability to do work or to produce heat, okay? And in chemistry, like I said earlier, it really refers to the sum of the potential energies and the kinetic energies of a given system that we're looking at. Now, when we're talking about potential energy in chemistry, we're really looking at bond energies, right? And then if you look at this word kinetic, moving energy, in chemistry, that is oftentimes associated with temperature. Remember, temperature and kinetic energy are directly proportional because the temperature is going to affect the movement of the molecules. Anyway, let's go ahead and look at potential energy in terms of how we would define that in a chemical sense. Now, we've learned that potential energy is the energy associated with something by virtue of its position. Now, when we talk about chemistry, what we're really looking at is the energy stored, the potential stored in the bonds. Well, when we go to break bonds or separate bonds, okay, you have to understand that the potential energy is going to be raised within that system because energy is going to be added into that system to overcome the forces that are holding those atoms together. In other words, potential energy is going to be raised as energy is being added into the system to break those bonds. Well, the converse is true. When atoms are going to form a bond, the Coulombic attraction between those two atoms is going to result in an energy that is being released subsequently that is going to lower the potential energy of the thing we're looking at. Now, kinetic energy is moving energy or energy in motion. And when, again, think about this from a chemical sense, what do you think that means? Well, when you have atoms and molecules and compounds, they're moving, they're vibrating. And we learned in a previous unit this concept of translational, rotational, and vibrational motions of the atoms and the subatomic particles that make up those atoms. So when we talk about this moving energy, this kinetic energy, that's kind of what we're looking at here. Now, there's some units of energy that you're going to need to know. If you had first year chemistry, some of this will look familiar. If you've had health class, this will look familiar. There are many units of energy, and here they are. So go ahead and jot these down in this space. 1 calorie, does that sound familiar? Yes, that's right. It's comparable to the calories in your food, right? Why do you think food labels identify the caloric intake of the food you're eating? Well, calories translate to, you ready? energy. So one big calorie, and you can see here that the C in this case is uppercase. That's going to be set equal to one, what we would call kilocalorie, okay? And you can also abbreviate that kcal. Another unit of energy that you need to know, or conversion, if you will, 1 kilocalorie, okay, kcal. And you guys know kilo is 1,000, right? So keep that in mind. So what would 1 kilocalorie equal? It would be 1,000 small c calories. It is the big C calories, you guys, that are on your food labels. You have one big cal is going to be equal to 1,000 small calories. Now, when you're talking about calories, you guys, you're going to talk a lot about nutrition. You're going to definitely hear this and see this come up a little bit. But the big unit in chemistry is a joule. And so 1 joule, and you spell it as Joule, is equal to 0.2390 little calories. So a joule is a measurement of energy, and that is the most common and what we're going to see the most here in our concepts that we're learning. So 1 small calorie, how about this one? You got one more here. 1 small calorie is equal to 4.184 joules. And lastly, we have something called a kilowatt hour. So here are just some standard common energy conversions that you need to know. Okay, so what is thermodynamics? Thermodynamics is literally the study of energy and its interconversions, or the exchanges. When in chemistry we are talking about the thing we're studying, we're oftentimes talking about the system, okay? So the system is the specific area in the universe that we're focusing on. It's our experiment, it's our investigation, it's the thing we're actually looking at. So anything that is not directly related to the system, anything else around it would be referred to as the surroundings. So everything that is not intrinsically a part of the system is referred to as the surrounding. By looking at this image here, you've got 3 scenarios. And oftentimes you might hear of an open system or a closed system. And even here too, we have something called an isolated system. Now, what this graphic is showing you is it's giving you a scenario of what the system and surroundings are in an open system. And that's the first image here. And this would be anything that's in that box right here, you guys. Anything that's in this box would be considered the thing we're studying, the system. And when the system is open, matter and energy in the form of work or heat are free to exchange with the surroundings. So this could be a chemical reaction that you're doing inside a flask, and that flask is not stoppered. It's opened, and therefore the chemistry inside that flask, if any heat is produced, it's free to escape the flask into the surroundings. So that's what we would qualify as an open system. Then you have something, and this is quite common when running experiments involving gases, is a closed system. And you probably can infer by the words what that means. This would be a situation where we are literally putting a lid on something or containing it. And you can see here that if we are in a closed system, that energy, usually in the form of heat, is free to exchange between the system itself and the outside surroundings, but matter is not, okay? The actual physical aspects of something cannot leave, okay? Like if gas molecules are being produced, for example, inside a closed system, gas molecules could not leave that closed system because it's being capped off or it's closed somehow. Now, an isolated system is a little different. You can almost think of like a coffee cup. This is actually a situation, or a coffee mug, one of those thermoses that where you put ice in, and the ice would stay for like 12 hours. And same thing, if you put hot coffee in there and put a lid on it, your coffee's still hot several hours later. Isolated systems, insulation to help reduce the energy exchange between system and surroundings, and also no matter can leave, okay? So one of the things about a system and a surrounding is that in order to understand really what's happening here in terms of energy exchange, and in any question that you're given, they would specify if it's an open system or closed system, because those two are really the big ones, right? But what we can quantify now is that if we're looking at the energy of a system, okay, And let's go ahead and set that equal to the energy of the surroundings, all right? So one thing that we can do is when we set these equal to each other, think about what's going on here. And let's just give an example. If you're considering the energy from the surroundings, okay, so not the actual thing you're identifying, but something close to it or around it. Now, an example could be you're frying an egg. The egg itself is the system, but the hot frying pan would be the surroundings, right? Well, if the surroundings in that hot frying pan are releasing heat to the system or to the egg, you're going to cook that egg. So it's fair to say that when energy is released, and it can be released either by the system or the surrounding, it doesn't matter. But in this case, if energy is released, let's say by the surroundings, this as an example, by surroundings, then this is going to be the same amount of energy that's absorbed by the system. So go ahead and take a look at the symbol that I would use. If energy is being released from the surroundings, that would be equal to the same amount of energy being absorbed by the system, right? And the opposite is true. So let me go ahead and finish writing that. Okay, great. Let's keep going, you guys. We're going to talk about an endothermic reaction and exothermic reaction in this unit. Really quick, before I read the definitions, look at these prefixes, endo and exo. Okay, I'm just going to tell you right now the prefix endo means in and exo means out. So let's see if we could take those prefixes and make sense of what these are. Okay, so what do you think endothermic means based off of these prefixes? Endothermic reactions are absorbing energy into the system. Exothermic reactions are releasing energy by the system. Okay, so again, endothermic reactions are absorbing energy from the surroundings and bringing it into the system. And when that happens, things will feel cold to the touch. Okay, now the opposite is true. In an exothermic reaction, energy from the system is being released to the surroundings. It's giving off energy, it's giving off heat, whatever it may be. So in an exothermic reaction, you will feel heat coming from these types of reactions. So let's take a second and look at energy diagrams that would represent an endothermic and an exothermic reaction. Now, you'll see these pop up quite a bit in chemistry. Again, we call these energy diagrams. Sometimes you'll hear them called reaction progress diagrams. And in some cases, they look very similar to something called reaction coordinate diagrams. So again, many synonyms, just like always, right? So let's take a look at the diagram on the left. And up here, go ahead and label this. This would be an example of the energy process of an endothermic reaction. As a quick reminder, the endothermic reaction is actually going to take heat from the surroundings, bring them into the system that you're studying, and it's going to actually be cold to the touch. Okay? The exothermic diagram is the one on the right. So why don't you go ahead and title diagram B exothermic. Again, as a quick reminder, exothermic diagrams are going to generate heat in the system and release them out into the surroundings. And so what you should see here is a representation of the potential energy that describes that. In the left diagram, the endothermic one, you're going to start off as your reactants. And as the time progresses or the reaction progresses, the reactants will need to overcome the activation energy. You should label this. The activation energy for this left diagram, the endothermic reaction, is actually just this hump here. It's this tiny little portion that I've labeled the activation energy. Now, the other thing that might look a little odd to you is this delta H. We haven't talked about that yet. We're getting ready to. That's actually the first law of thermodynamics, is this value H, which we call enthalpy, and we'll get to it in just a second. Ultimately, though, in an endothermic diagram, we're going to, again, the system is going to absorb energy. So energy is going to increase we're going to eventually get to the point where we reach the activated complex. Do you guys remember that? And as if the activated complex successfully forms, then the reaction would proceed. Now notice that the potential energy of the products is going to be higher than that initially of the reactants in an endothermic reaction. And so down below, I'm going to annotate this graph here really quick, describing what I'm seeing. And there you go. Heat energy is being absorbed into the system by the surroundings, and the end products are going to have a higher potential energy than the starting reactants. Now, look at the difference in the exothermic diagram. Our reactants are going to start at a higher potential energy than the final products, all right? And again, you're going to have this activated complex form after the reactants overcome and reach the activation energy. Once that activation energy and the activated complex is released, the reaction will proceed, at which point energy is going to be released over here, and the products are formed. So again, I'm going to just quickly annotate what I'm seeing here. Okay, let's break into some more definitions, some more vocabulary here, and let me go pretty quick. We've got some laws of thermodynamics we need to cover. We've got a first, second, and third law here. I want you to know there is actually a 0th law of thermodynamics. It's not within the scope of the course, so I'm not going to talk about it here, but for those of you who are interested, there's a lot more to thermodynamics and thermochemistry than what we're going to cover here in this unit. Anyway, the first law of thermodynamics, which arguably is the most talked about, it's probably what you learned in first year chemistry, but you would know that this definition should sound familiar. Energy is not created nor destroyed. Okay, it simply implies that there is simply a change within the system. Okay, the energy transfer in the system is equal. Okay, and so the second law of thermodynamics actually is going to come later in the unit when we talk about something called entropy. And this is basically defining how the universe is going to be constantly increasing and tends to go towards disorder and chaos. Okay. And then the third law we're going to maybe just briefly touch on, and that is how the entropy of a perfect crystal, so a crystalline structure at 0 Kelvin, would be equal to 0 in value. So let me keep going here. When we talk about thermodynamics, we have to talk about heat. You've heard me say it a couple times. We're going to use lowercase q to represent heat here. In the next video, I'm going to give you an equation so you can actually calculate heat, or calculate Q, if you will. Now, what is heat defined as? It's where you have two systems that have varying temperatures, and when they come into thermal contact with each other, you will simply see a transfer of that heat energy. And of course, just like you've learned in biology, the warmer object will transfer heat energy to the cooler object, okay? Now, when we talk about temperature, nothing new to you guys, we're going to use a capital T to represent temperature. Again, this is proportional to the average kinetic energy. You've heard me say that multiple times. I also like to say you heat them up, you speed them up, okay? Now, when we talk about the first law of thermodynamics, that's when we're talking all about enthalpy. We're going to say enthalpy. Say it with me, enthalpy, and we're going to use capital H to represent enthalpy. Now, enthalpy is very similar to heat, all right? In fact, it is equal to heat at a constant pressure. Needless to say, it's described as the flow of energy or the heat exchange in a chemical reaction. So if you look at the reactants and what you're starting with, and then at the end of the day, you look at the products and what has been produced, what is the heat exchange that went on between the breaking of those bonds and the reforming of those bonds to form the products? Enthalpy is going to describe that, all right? And so you can actually calculate the enthalpies of many types of reactions. I've just listed a couple here. The most common one is going to, in AP chemistry, is the enthalpy of reaction. And you guys, all this are enthalpy values given to you. They're either given to you in the problem, or you would need to look them up in appendix. You can look them up online. But enthalpy values for all known common compounds are given and known. You have to look them up, or they need to be given to you, like I said. And simply what you would do is just use these enthalpies to calculate the enthalpy of the overall reaction. Now, you can have an enthalpy of combustion, an enthalpy of formation, an enthalpy of fusion, an enthalpy of vaporization. Fusion and vaporization, rather, are literally just state changes. So in this case, you would be making calculations and determining the heat exchange when you do a phase change. If you did like an enthalpy of combustion up here, of course, you'd be specifically talking about heat exchange in a combustion reaction. Again, enthalpies of reaction are going to be the most common type. You're going to be given those values, and in just a second, we'll do lots of examples. Another vocabulary word you need to know is entropy. We're going to use S to represent entropy. Go ahead, say it with me. Entropy. This is defined as the disorder of a system where actually disorder is favored. This is going to be your favorite law when describing to your parents why your room is trashed at the end of the week, right? Started off nice and clean, and then it lends towards disaster and chaos by the end of the week. Now, nature tends towards chaos, believe it or not. It is actually simply defined as the dispersal of matter and energy, okay? And so if you have an increase in entropy, you're going to have more of a positive value, more chaos. If you have a decrease in entropy, you're going to have a negative S value. One other vocabulary word here, Gibbs free energy, designated as a capital G. Gibbs free energy is the energy or the energy criteria for determining whether a reaction is going to thermodynamically be favorable or not. Is it going to happen spontaneously or not? And so what you guys are going to do is later in the unit, you'll be given a formula for Gibbs free energy to calculate the value of G. And based on that value, that will tell you whether it's a positive value or negative value. It will tell you if the reaction is spontaneous or thermodynamically favorable or not. Okay, let's keep going. Work, obviously, you guys know the definition, but in a chemical sense, which is lowercase w, it's when we define a force acting over a distance. This is really common in physics. You're going to see an equation that's given to you here. We'll talk about a little bit more detail, but this is when really when gases are involved, you'll talk about work. And then you have standard conditions. Please don't confuse this with STP, which is standard temperature pressure. So standard temperature pressure, STP, is not the same as standard conditions. When something or chemistry is being held at STP, this value right here, it is being held at 0 degrees Celsius and 1 atmosphere. Now, I don't know if you guys know how cold 0 degrees Celsius is. It's cold. It's freezing. It literally is freezing. It's 32 degrees Fahrenheit. So what they have done is created another set of conditions that they call standard conditions. And standard conditions are basically experiments that are ran at, you ready? 1 atmosphere at 25 degrees Celsius. So much more comfortable. Don't forget, a standard condition, again, is 1 atmosphere, 25 degrees Celsius. And if you're dealing with any solutions, you're going to be dealing with the standard 1 molar concentration of that solution. If you, by any chance, happen to see these little not symbols here, I just highlighted it. When I say not, I'm talking about NaUGHT. What that means is you're given the values or calculating the values at standard condition. So the not symbol indicated next to Gibbs free energy, enthalpy, or entropy simply indicates that that condition is at standard conditions. Okay, now let's talk about energy and work. Okay, energy is defined again as the ability to do work, and you can see here is the equation for energy. The change in energy is going to be equal to Q plus W, so heat plus work. Now we have to pay attention to signs here. If heat has a positive sign, okay, I'm going to go ahead and circle this right here. If you're given a positive value for heat, what that means is heat is being absorbed from the surroundings into the systems. Whereas if the heat value is negative, then what that means is that the system is releasing that heat. Okay, let's take a look at the signs for work for lowercase w. If you have a positive work value, okay, if it's a positive number, what that means is that work is done on the system by the surroundings. Whereas conversely, if it's a negative work value, work is done by the system to the surroundings. Okay, and so really you've got to pay attention to signs here. We're going to get some practice in just a second. And here is your equation for work. You can calculate work, and it's equal to the negative pressure times the change in volume. It's a good time to speak right now about this delta symbol. It literally means change in. You've probably seen it before. When you're calculating the change in something, you're always going to take the final value and subtract from initial value. Okay, now let's do exercise 1 as a problem. Always start off and write your givens. So let's read the problem. We're going to calculate the change in energy for a system undergoing an exothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. So you can see here an endothermic process. Okay, an endothermic process is going to end up, your Q value for an endothermic process is going to be positive. Remember, if you go back up here to Q, heat is being absorbed from the surroundings into the system. And so Q is going to be a positive value. And then it says that 15.6 kilojoules of heat is going to flow. So heat, of course, is Q. So now we know our Q value is positive 15.6 kilojoules. And then it's telling us that we have 1.4 kilojoules of work is done on the system. If work is being done on the system, that's going to be a positive value. So W equals positive 1.4 kilojoules. And then, of course, to calculate the change in energy, one way to do it would be to add heat plus work. And we know that both of them are positive values. And so as I'm writing this right here, be thinking about what the signs of each of these mean. It's representing where the transfers are going, where the transfer of heat is coming and going, or where the transfer of work is coming and going. That's what the signage here means. When I add these two together, I get 17 kilojoules of energy. The change of energy that's being done to that system is 17 kilojoules. Now you're used to joules, but that's okay. Kilojoules works as well. Exercise 2, calculate the work associated with the expansion of a gas when we go from 46 liters to 64 liters at a constant external pressure of 15 atmospheres. Again, it's always in the good habit to write your givens. You do know that delta means final minus initial. And if you were given an initial volume of 46 liters, you were given a final volume of 64 liters. It definitely looks like the volume increased here, right? It's asking us to calculate what would the work be. And by the way, they gave us pressure, and that was 15 atmospheres. And so work done by the system onto the surroundings, okay? Because that's what's going on here. If you read it, the work that is done by the system onto the surroundings would result in a negative work value, okay? Yeah, and so what you're going to have here is work is going to equal to negative pressure times the change in volume. You know that the pressure is 15 atmospheres, and then the delta V, final minus initial, is 64 liters minus 46 liters. Do the calculation. Don't forget that negative sign. You're going to get 270, and don't forget liters times liters atmospheres is the correct way to say it. Again, so what does this mean? Work is done by system to surroundings. Okay. Exercise 3, we're going to do in class. Exercise 3, we will go ahead and do in class, or either Monday or in person. And that's basically going to conclude this first lecture here. Why don't you do me a favor and go ahead and make some note cards with these definitions if you are struggling with any of them. Go back and rewatch this podcast. I also like to mention that if you want a deeper dive into some of these vocabulary words, I would encourage you to pull out your AP Chemistry textbook and go to the unit titled Thermochemistry, and you can get a lot more information there. All right, thank you so much for watching. Bye-bye.